potassium solid?
And then
Yields.
potassium ions.
Potassium ions.
And electrons.
And an electron. Okay, let's label this one first. What is potassium solid?
Reducing.
What is potassium ion?
Oxidizing.
Yeah, it's a conjugate oxide. Okay, what's the other equation?
Two water liquids.
Two water liquids
Plus 2 electrons.
plus 2 electrons
Yields.
yield
Hydrogen gas.
hydrogen gas
2 hydroxide.
plus 2 hydroxide. Okay, what is water?
That's your oxidizing.
Okay, and then that means hydrogen and hydroxide must be your. Okay, we do this now to make figuring out the driving force easier. Yeah. Okay, what's the next step?
Balance number electrons.
Yes, so what do we need to do to get it balanced? We need to multiply it by what? 2. So we're going to have two potassiums. Right? Okay. Two potassium ions and 2 electrons. So now it's balanced, 2 electrons and 2 electrons. And then what do we do? We need the electrons to cancel, remember? Here. And then what do we do? Well, maybe you haven't had a chance to review the example we did yesterday. But we add them together. And so when we add them together, we have 2 potassium solid plus 2 H2O liquid yields 2 potassium ions plus H2 gas plus 2 hydroxide. And then we look for a driving force. So this is our reducing agent, this is our oxidizing agent, this is our oxidizing agent, this is our reducing agent. And then we compare the oxidizing agents and reducing agents. So water versus potassium, water is stronger, potassium ion is weaker. Potassium metal versus hydrogen, potassium metal is stronger, hydrogen is weaker. So we have driving force here. And so this reaction does occur. Potassium is going to make hydrogen gas. Hydrogen gas is quite explosive. So let's take a look at this reaction. Redox reactions tend to be much more energetic than sodium in water. Starts off slow, goes off with a bang. Okay. This is potassium. Potassium reacts much more violently than sodium does. Slow-mo. Sodium was off to a slow start. Potassium just went off right away. Redox tends to be quite violent because of the energetics of this, In metathesis and double replacement reactions, there's no change in we have potassium ions, we end up with potassium ions. There's no change in the oxidation state. In acid base, there's no change in the oxidation state. It's just, looking at combinations. But in redox, there's a change in the oxidation state, which makes the reactions quite a bit more violent. sometimes there's species that don't occur, you know, on it. So ethanol, potassium permanganate, and hydrochloric acid. When you look at this, what comes to mind? You know, if you look at this mixture, well, I know something. When I look at that mixture, I see something that's quite reactive. What do you see that's quite reactive?
That's just the product.
Well, you know, let's break it down into this. Ethanol, the major species, when I do the inventory, it looks like this. If I'm looking for redox, ethanol just stays ethanol. Potassium permanganate is going to break up into potassium ions. Anything special about potassium ions and redox?
Strong.
Potassium metal is, but what about potassium ion? Potassium ion is a conjugate of strong reducer, so nothing special. Potassium ions are very unreactive in redox, so I don't really worry too much about that. What about permanganate?
Strong oxidizer.
Permanganate is a strong oxidizer, so I gotta watch out. H plus is the moderate oxidizer. Chloride. It's chloride. Weak reducer, and water. Water is a weak reducer and a weak oxidizer, so nothing special. So the thing that really stands out to me is permanganate. Permanganate's a strong oxidizer. Now, the other thing that stands out about this is this. Ethanol. Is ethanol flammable? Yeah, ethanol's flammable. Ethanol, you can burn this stuff. What do you need to burn ethanol? You need an oxidizer like, in order to burn ethanol, you need, in a combustion reaction, you need, not CO2, those are the products. It's going to form H2O and CO2, but it's ethanol plus oxygen forms CO2 and water. Okay, so ethanol's acting as a reducing agent, right? And it's a good reducing agent, and oxygen's acting as the oxidizing agent. Oxygen's, but in order to burn ethanol, you have to have oxygen. Can you burn ethanol in the absence of oxygen? Yes, you can. Yes, you can, because oxygen is not the only oxidizer around. There are many oxidizers around. And so we don't even need oxygen to burn ethanol. All we need is a decent oxidizer. Well, oxygen is a decent oxidizer. Oxygen's a decent oxidizer here, but is it the best? No, there's more powerful oxidizers like permanganate. So when I see this reaction, I think potential explosion. Potential explosion because, you know, if ethanol ignites, we can get a bad fire or possibly an explosion. You know? You've seen, have you seen like even methane? Methane explosions, have you seen that? Yeah, you'd be surprised about maybe about the damage that they could do. That used to be an apartment building there. Can you believe that? 4 people died in that explosion. that was with methane and oxygen. Methane. Oxygen. Is oxygen the most powerful oxidizer? No. There's more powerful oxidizers. So if you're dealing with a more powerful oxidizer, you better watch out. And you better be careful because you could have a nasty reaction occur. Well, methane is electron rich. Methane is quite electron rich. How do I know? Well, how I know that methane's electron rich? Oxidizers are electron poor, right? What's the, why is permanganate? Permanganate doesn't seem electron poor, it's got a negative charge. Why is permanganate a good oxidizer? It's not because of the negative charge, it's because of the manganese. The manganese is +7. That's why. Methane is a good reducer because you know what carbon is in methane? Carbon is not plus, -4. It's a good reducer. Methane's a great reducer. It's got a lot of electrons. What about ethanol? Well, for ethanol, ethanol is a great reducer too. For ethanol, it's a little bit more tricky because we have multiple carbons there. So for ethanol, the best way of determining the oxidation state is from the Lewis structure. So if we look at the Lewis structure here, remember there are different ways, 3 ways of counting electrons. Tell me the 3 ways of counting electrons. There are more than 3 ways, but 3 main ways of counting electrons. We count the electrons as using the octet rule. Octet. We can count the electrons using you guys remember doing this? And what was that called? Did this a whole bunch with Lewis structures. What was that called? Counting electrons with Lewis structures. Can you guys, the final is going to be coming up. Can you guys start reviewing for the final? Because to cram it all in one night is not going to be possible. It's not doable to cram. It's too much information. So you want to start reviewing sooner is better. You remember doing all that stuff with the Lewis structures? What were you calculating? Formal charge, right. Formal charge. That's what we were calculating. And then we did 3 ways of counting electrons that day. What was the 3rd way? Oxidation state. So we're going to do oxidation state. And for oxidation state, how did we do it? Well, we divided it, winner take all. Who's the winner? The one with the higher electronegativity, unless it's a tie. Carbon versus carbon is going to be a tie. So how many electrons does carbon end up with? 2, 4, 6, 7. It's supposed to have 4. This means the oxidation state on this carbon is -3. It has 7 electrons. It's supposed to have 4. It has 3 extra electrons, 3 extra negative charges there. Well, that's close to this. Methane's -4. We can do methane the same way, winner take all. Methane, carbon ends up with all the electrons, it's more electronegative, so it gets 8 electrons. Hydrogen ends up losing. Each hydrogen's +1. Here, when we do oxidation state, I write the 1. When we do formal charge, I just write plus. All right, over here, winner take all. Well, oxygen versus carbon, who's going to win? Oxygen wins. And so carbon ends up with 2, 4, 5. This carbon's different. This carbon's a -1. So this carbon is more electron rich. This one's more methane-like. This oxygen's going to end up at a -2. And then the hydrogens are all +1. And so ethanol is electron rich. We'll burn the stuff. How about CO2? Is CO2 electron rich? What's the oxidation state of carbon in CO2? Or how about let's do it like this? Oxygen should be no oxidation states. Oxidation states. Oxygen is -2, which means carbon is +4. You can go back. I'm not going to go through it again. You can go back and look at it if you want, or just skip this with the final. But you'll need this for Chem 1A. But I don't know how many points you sacrifice on this. But this is going to be +4. What's special about +4 on carbon? I don't know if you guys recall. Do you remember carbon? This is called carbon dioxide. Do you remember me ever talking about this carbon trioxide? What did I say about carbon trioxide?
It's not possible.
It's not possible. Why is it not possible? You can have a bond to 3 oxygens. It's not possible for another reason.
Carbon's oxidation can go past can go higher than
It can't go higher than +4. It can go lower than +4, like carbon monoxide is lower, that's +2. But it's not going to go higher than that, right? And so this is what we call, when we burn ethanol, we burn it completely and we form CO2. That's why it stops at CO2, it doesn't go to CO3. Now, for this, I see a reaction. Basically, this is the reaction I see. This is going to be like a combustion reaction, but we're using a more powerful oxidizer than oxygen. We're using permanganate. Now, permanganate is going to need one more ingredient. What else does permanganate need? H+, which is acid. And so we have H+ here from the hydrochloric acid. And so when we have a combination of permanganate with acid, watch out, that's a powerful oxidizer. Even though ethanol is not on the chart, ethanol is one of those organics. A lot of organics are flammable, and so this is one of those organics that are flammable. And so I see a potential explosion here when I mix ethanol and water. Now, to figure out what happens in this particular reaction, we can talk about that. Although, I'll stop talking here. We're going to continue redox, but why don't you work on the quiz?